Hello everyone, it's Mr. Wolfe here, and in this video I'm going to be introducing constructing explanations with energy. Alright, so in class, we had a demo set up where there was two ramps. Notice that there's obviously a difference in steepness of the ramps, but we dropped the cars from the same height. And we asked the question, how are the velocities of these cars going to compare when they're at the very bottom of the ramp right here? And by the way, this ramp is a frictionless ramp. So the options were, this one's going to go faster, this one's going to go faster, or they're going to have the same velocity. So really quickly, pause the video, think about it for a few seconds, and make a prediction. All right, so at this point, you should have made your prediction. And if you haven't, please pause the video, answer the question. All right, so we can't test it in this video, but what ended up happening is this car went down the ramp, and it had a velocity of 2.18 meters per second, at least in one of my classes. Right? And then this one went down the ramp, and it had a velocity of 2.19 meters per second. That is not a huge difference. We could say that these velocities are essentially the same, right? And that kind of goes against what some people, what of your predictions or your classmates' predictions was in class. As they said, hey, look, this is steeper. It's going to go at a faster velocity, and intuitively, it kind of seems like that would happen. But one thing that's important is this is a frictionless ramp, right? So how could we explain these results? Well, we're going to make our LOLs and then explain our LOLs, and that'll help us get to the claim that they will have the same speed at the bottom of the ramp. Okay, so when it comes to constructing explanation, I'm going to go through an example here, but I want you to all be using this template, especially in the beginning when you need support. You could get this on Canvas. So there's a few things here in terms of like when, and by the way, make sure to watch that other video if you weren't here for work. On when energy would enter or go into our system, right? What would cause that? So there's some info here. But for constructing explanations, this is the stuff I really want you to be paying attention to. So we're going to draw our LOLs. We've been doing that, but then we have to explain our LOLs. And how that's going to work is that there's two success criteria. The first is you just kind of say what you drew in your model. That's it. So if you drew UG, you'd be like, hey, I drew UG. And if sometimes you have to compare the two, many times you have to compare the two. So you might say, hey, I drew the same UG in the beginning. That's all describing the model is. All right? But you have to give a reason on why you did that. Like, what physics concept do you know? All right? And by the way, here are the physics concepts that you would use. Right? How do mass and velocity affect kinetic energy? How do mass and height affect potential energy? And how do force and distance affect work? Also, just this understanding that you cannot create or destroy energy, but it can enter or leave your system. All right? So let's look at an example of this. All right. Sometimes students will just draw the LOLs and then they'll do the reasoning. I think it could be helpful sometimes to kind of do both at the same time, and I'm going to show that example in this video, but you could always do it in whatever order you'd like. All right. So I'm going to actually first start with the physics concepts. Right. So like this physics concept. So this is why I'm drawing the model the way I am. All right. So if I look at the very beginning, this cart the carts have, and by the way, in order to answer this question above, you need to look at, well, if it's asking about speed, remember that's velocity, and the equation k equals 1/2 mv squared, right, is my equation that involves velocity. So I need to look at k, kinetic energy, to answer my question, but my cart's going to have k is going to show up at the end in my scenario, so I know I'm going to look at the LOL, the end of my LOL, to answer my question. Right, so just kind of giving you a way to frame how you're going to explain everything. I'm going to start on the first L, and I'm going to say, okay, same mass and height of the car. Right, that's my physics concept. So what do I draw for my LOL? Same UG, and that's what we'll do. All right, same UG over here, same UG over here. If I wanted to, I could also say no velocity, so no K, right? The important thing, I think, is sometimes just showing the energy that you do have in some instances. All right, so now I'm going to describe the O. And in the problem, there's no outside forces because this is a frictionless ramp, so no forces, which means no work. All right. You could also say something like no energy enters or leaves the system, because that's what work is. But I'm not going to draw anything here because I know this is a frictionless ramp. All right. So then at the bottom, all right, I could say like no height. This is for that last L. So no UG. All right. So I just literally just won't draw anything for UG right here or right here. All right. But I know I can't create or destroy energy. Right. But E is conserved, which just means it can't be created or destroyed. So all energy transformed to K. All right. So I'm just kind of showing like, hey, look at like it's the same amount, or I could, better yet, I'm going to say same amount of E transformed to K. Essentially saying that, hey, there were 4 blocks here, 4 blocks here, right at the bottom of the hill, that same amount, if there was no friction, is going to get transformed into kinetic energy here and kinetic energy right here as well. All right. So I've explained my LOLs, but my question is about speed. And I really haven't talked about velocity at all, besides just right here that there was no velocity. So then I have to work on my concluding statement. Right? What I like to do is I like to use, all right, my physics concepts, my equation, and then this template to help me out. So what I'm saying there is that here's my equation. Maybe I'll do this in green. K equals 1/2 mv squared. All right. I like to box in a variable if it's constant. My mass, all right, same car, so same mass is boxed in. That's not going to change. And I just found from my LOLs, this is why we do the LOLs, that this K is boxed in as well, which means it's the same amount of K, right? So in my equation, if these variables are the same, there's no way for this velocity to change as well. If velocity did change, then that means that mass or kinetic energy would have to change. And because we know for a fact that they're stuck there, that means velocity is stuck as well. Right? Another way to describe that is with this concluding statement. Right? Because, and then I always like to start off with like what stays constant, because mass stays constant when, or better yet, if you look at this right here, this is usually if something's increasing or decreasing. All right, doesn't mean we could still use this. We just really can't use it verbatim, all right? Because mass stays constant, and I might just say, and K stays constant, all right? Then the velocities must be the same. And then notice that my concluding statement automatically looks pretty dang similar to the claim that I ended up choosing. All right. So really all the contracting explanations are is, yeah, they could sometimes maybe seem a little bit wordy, but I'm not looking for a huge essay. I'm fine with you writing things out like this. That's totally okay with me. You're really just trying to convince me, why did you draw the LOLs the way you did? Like, you have to communicate that. And honestly, I think it's really helpful for understanding the concepts, because instead of just guessing, you have to write out why you did what you did, and that helps you make sure that, yeah, like this sounds right. All right, thanks for watching.